So, in today's lesson, we're going to talk about polarity, as Bill and I said, bond of both polar bonds. So when we're talking about polarity, the big thing that we're going to be talking about are covalent bonds. To remind you of what covalent bonds are, remember covalent, co meaning two or more, non-metals bonded together. These non-metals, remember, are bonded by the sharing of electrons. When we talk about polarity, we're going to be focusing on the sharing, the aspect of unequal sharing. So when we look at hydrogen, and we say that it has a low affinity for electrons, another term that we can use for very low affinity is electronegativity. We know that electronegativity is an element's ability to gain or lose an electron. So when we're looking at hydrogen, we know hydrogen actually has a very low electronegativity. Well, we know oxygen has a very high electronegativity. Remembering the trend on the periodic table, as we go up and to the right, we have an increase in electronegativity. So what do you think the bond between a hydrogen and an oxygen would actually look like? Do you think there would be equal sharing of electrons or unequal sharing of electrons? As a result of this unequal sharing of electrons, would there be a slightly positive end of the bond and a slightly negative end of the bond? When we look at polarity, we look at polarity as nonpolar covalent bonds and polar covalent bonds. Nonpolar covalent bonds we know are when electrons are shared equally. We know that these electrons are sharing these atoms are sharing these electrons equally between the two because they both have the exact same electronegativity. So if you were to look at table S and subtract the two electronegativities, you would have a net result of 0. When they're between the same atoms, we know that our electronegativity will be 0. When you do not have the same elements, you know that the difference will no longer be 0. Looking at these nonpolar covalent bonds, you can see the center of the positive and negative charge. Think of it like tug of war. If two people are pulling on the rope with the exact same strength, the flag would stay in the middle. When you have two people with different strengths pulling on the flag, the one with the more strength, in our case, the higher electronegativity, would be the victor, pulling the flag more towards their side of the court. Opposite of nonpolar covalent bonds are polar covalent bonds. Polar covalent bonds are when electrons are shared unequally, so we actually have a difference in electronegativity. Based off from that difference, we now have a slight positive and a slightly negative end of our bond. These two symbols here represent slightly positive and slightly negative. What they create is what we call polar ends, which creates a dipole, or a movement of our electrons. Difference in electronegativity, by subtracting the two values found on table S, we can determine how polar a bond actually is. The larger the difference in electronegativity, the more polar that bond can be. Looking at water, for instance, oxygen we know has a higher electronegativity than that of hydrogen, thus causing the electrons to spend a majority of their time around the oxygen instead of the hydrogen. The result, a slightly negative charge towards the side of the oxygen and a slightly positive charge on the side of the hydrogens. Looking at this with electron density clouds, we look at two hydrogen atoms, I should say, bonded together. Based off from the bonding of these two hydrogens, you can see that there's an equal dispersion of the electrons. Based off from that, we have a dipole moment that equals 0. Polar molecules, we can see that there is actually a dipole moment or movement of the electrons. The electrons are going from the hydrogen to the fluorine. Fluorine having the largest electronegativity, hydrogen having a much lower electronegativity. You can see, based off from the large difference, a large movement in electrons, thus creating a slightly positive and slightly negative region on the bond. This arrow here shows the movement of the electrons, leaving the plus sign, the positive end, and going towards the slightly negative end. So in comparison, when you're looking at ionic versus covalent versus polar covalent, ionic we know is the complete net transfer of electrons. Covalent we know is the equal sharing, or non-polar covalent is the equal sharing of electrons. Where our last one is polar covalent, we know that there is an unequal sharing of electrons, thus creating a partially positive and partially negative aspect of the bond. When we look at polarity, in order to determine how polar something is, all we do is take the difference in electronegativity. Using table S, you can find the actual values of hydrogen and chlorine and subtract them from one another. When you subtract the two elements, the electronegativity is determined, and thus anything greater than 0 determining the overall polarity. Any difference equals a polar bond because of the unequal sharing. The more the difference, the more the polarity. Remember, again, the arrow shows the direction in which the electron cloud is being pulled, thus leaving the positive aspect, and now the new slightly negative aspect of our bond. When you actually calculate these in your notes, you can see that the electronegativity of the hydrogen is 2.2, the oxygen is 3.4, which I obtained from table S. Once subtracted, I have a difference of 1.2, therefore I know this is indeed a polar bond, with a slightly positive region at the hydrogen and a slightly negative at the oxygen. Your next example in your notes is a hydrogen to hydrogen bond. Looking at your hydrogen to hydrogen bond, we know that hydrogen has an electronegativity of 2.2. 2.2 minus 2.2 results in 0, therefore giving us a non-polar covalent bond. Our last example is between nitrogen and oxygen. Nitrogen has an electronegativity of 3.0, while oxygen has an electronegativity of 3.4. Subtracting the two, we have a difference of 0.4, thus leaving the slightly positive region on the lower electronegativity of the nitrogen and our slightly negative on the higher value of our oxygen. This is indeed a polar bond, but in comparison, not as polar as that between oxygen and hydrogen.